Now you must wonder that, all right, why do we need to know the force boundary condition? Well, what if you have a cantilever beam or the cantilever column, just like one of the columns that we studied in the past, remember? There's one example. The force is applied at the cantilever, which I think is example 9, right? There are two P's acting on basically a cantilever column. So in that case, that means what? That means there's actually free end. So this is a free end. That means there's nothing. In this case, if the free end, the second order derivative is what? The second order derivative must be 0 because second order derivative is related to moment, and at free end, there's no moment. At free end, there's no shear, right? That also means what? Say third order derivative must be 0 at this point. Now, let me ask you this. What happens to the first order derivative? In this case, suppose it's a free end.
Not 0.
It will not be 0, right? So the first order derivative must not be 0. Because that means it's a free end. As long as you have any moments acting within the span of this column, the free end must be rotated. So the slope must not be 0. And for the same reason, deflection also will not be 0. Right? So in summary, we use the first order and the second order. I'm sorry, the zeroth order and the first order derivative of deflection as what we call displacement boundary condition. And we use the second order and the third order as the force boundary condition. So that is the, and I think it's more like a review. You probably have seen some of these from structural analysis, but this is just a quick review because in the next example, we're going to start using many of these in following examples. Okay, now we can start with example 10. And this example is so what is this example? This example is a simply supported beam subjected to uniformly distributed lateral loading. That means we have a structure like this. And the loading now is uniformly distributed. And it can be denoted by W of X. Of course, to create buckling, there must be axial force. So axial force acting at here, and consequently will produce a reaction force at the hinge, not the roller, at the hinge. Coordinate systems must be defined as soon as possible. So we define positive X and positive Y. And the vertical downward pointing, let it be a positive Y, and the right hand pointing, let it be positive X. And everything is as usual. As you know, we're going to have the total length to be capital L, and the E and I's are all the same. And the column still has its own EIs. What's our objective? Our objective is to find PCR, just like before. Now, from here, you remember the steps. And we usually combine the step 1 and step 2 together, right? By considering the deflection, then we take the free body diagram. So in this case, you can just define the deflection to be here, and this just to make our life easier. So suppose it buckles like this, and we look at the free body diagram. The free body diagram, of course, we have different choices, whether you go with the second order approach or the fourth order. So suppose we go with the second order. That is the approach we are more familiar, which means that you have to take one end, one support into account. And that means, suppose we take support from A, and A means from here. Actually, I don't like this to be A, suppose, because we're going to use integration constant as A. Why don't we just call it 1 and 2? Okay, like this. And by considering support 1 in the free body diagram, we have something like this. And you also have your X and Y going this way. This is your X, it's your Y. Your loading goes like this. And external force acting right here. Internal reaction here. This is support A. And what will be the direction of this internal moment? Is it clockwise or counterclockwise? Clockwise or counterclockwise?
Counterclockwise.
Counterclockwise, right? Because this is positive, this is the direction of positive moment. So it's counterclockwise. Now, what we have to do once we establish all these forces at support 1, there's no moment. There's only a horizontal force P. And so that's pretty much what we have, right? Then we just take the moment equilibrium, which is back to what point? Well, in fact, you can take the moment equilibrium with respect to any point you like. You can take at support A, you can take at the at whatever you cut it, which is somewhere like this. You can do either way, and the result will not be any difference. So suppose we take the at the support A. Okay, we take moment 1 must be 0, and by assuming that counterclockwise will be positive, this way we can use the positive expression of internal moment. So that will give us the expression of starting with the internal moment because this is positive. So which one is the internal moment? So let me just finish this one. This is the internal moment in the counterclockwise direction. And the moment produced by the force P is positive or negative, isn't it? Is negative, right? Because it produces clockwise rotation. So that is minus P times Y. And we also have what? We also have
moment produced by the distributed load.
yes. Well, actually, we missed one more thing, and we actually made a huge mistake here. Before we continue, if you look at here, what did we forget?
The reaction at 1.
Yes, we forgot about the reactions, because in this problem we have lateral vertical force, right? Even so, that value is very straightforward, but we forgot to formulate it. So this is next time. Please be careful before you start formulating your moment equilibrium expression. Make sure you consider all kind of forces. So this kind of mistake is definitely not a good practice. We forgot to consider the vertical force or vertical reactions at support 1 and support 2. So here, let's consider the reactions. At support 1, the vertical force is what?
WL over 2.
Very good. So that is WL divided by 2. At both ends, right? That's reaction. So that means here we should consider there's another vertical force, right? And that is WL over 2. Now, what about the cross-section when we cut it? And this cross-section that means if on the support is at the distance of x, because from here, from the end to this point here, this is denoted by x. If you have a reaction at support 1, at that cross-section when we cut it, is there a shear or not?
Yes.
Of course, there's a shear. Right? And what is the magnitude of the shear?
WX.
WX over 2.
Is whatever you have taken, right?
Oh, yeah, WX.
You have to consider the reaction from support 1. So that means from support 1, you have half of it. And it's going to lose the portion of W times X. So to achieve the vertical force equilibrium, the remaining part must be, should it be upward or downward?
Downward.
Downward, right? Because positive shear, so this is downward here. That means there must be downward shear here. And this one is what? The value is WL over 2 minus WX. Would you agree? Why WX? Because that's the total vertical force from the support 1 to the location of consideration. That means the summation of the vertical force at the top here is WX. So if you consider the vertical forces, right, then you achieve vertical summation Fy to be 0. Because Wx plus WL over 2 minus Wx equals to WL over 2. So that's all we make sure. That's why we know this value must be something like this. Now we can continue our moment equilibrium. So in this case, this moment will produce positive or negative moment. Is it positive or negative?
Negative.
Is negative, right? So that means you will write this part to be negative minus the force 2 minus Wx times what? Times x, right? That's the force times distance, correct? So that's one moment. But there's another force, which is the vertical force coming from the loading. And the loading will produce positive or negative moment.
Negative.
Also negative, right? So we have one here and the other one is a negative one. So that's negative minus Wx times, in this case, we're going to use the center of this distributed load, which you must know, have seen this in structural analysis, times x over 2, right? Then the whole thing has to be 0.